In this video, building on our previous discussion of kernels of ring homomorphisms, we'll give a brief introduction to ideals in rings. So ideals are going to play a really important part in the end of this course and also in 206B. So we'll talk about these a lot more over the next several lectures. But here I just want to give you the definition. So this is the definition from page 242 of Dummit and Foote. Let's say R is a ring, I is a subset of R, and little r is an element of the ring. We're going to write R times I to be the set of all things that are this one fixed element, little r, times A, where A goes through everything in the subset. And same thing on the right side, I times R, which is everything, which is of the form A times R, where A goes through the elements of the subset. So I really want to emphasize that multiplication in your ring R might not be commutative. So R times I and I times R might not be the same sets. All right, let's give this definition. A subset I of R is a left ideal of R if it's an additive subgroup of R and it's closed under left multiplication by elements from R. What does that mean? You take the subset R times I, and that has to be contained in I for any R in the ring. So let me emphasize one thing that this tells you is if you take R to be an element in I, then what you're saying is you take the product of any two elements in I and you land back in I. So in particular, this implies that I is closed under multiplication. So it's an additive subgroup of R closed under multiplication. In Dummit and Foote language, this makes I into a subring of R. But with Conrad's definitions, I doesn't get to be called a subring unless it contains the multiplicative identity of R. Okay, so that's left ideal. Corresponding thing, very, very similar. Right ideal, I is an additive subgroup of R, but instead of being closed under left multiplication by elements from R, you have to be closed under right multiplication by elements in R. That is, I times R is contained in I for all elements of the ring. All right, so we have left ideal, we have right ideal. By far the most important case in this course is going to be subsets I of R that are both left ideals and right ideals. Those are just called ideals. Or if we really want to emphasize that they're both left and right together, sometimes you'll see these referred to as two-sided ideals, but for the most part, I'll just say ideal. So as a first comment, if R is commutative, then it's clear that R times I and I times R are the same. So if you're closed under left multiplication by elements from R, you're also closed under right multiplication by elements of R. And any left or right ideal is automatically a two-sided ideal. So this distinction does play an important role for non-commutative rings, but that'll be less important for this course. Okay, so we'll give a lot more examples of ideals in the next few lectures, but here's one. So near the beginning of this lecture, we proved that if phi is a ring homomorphism from R to S, and you have alpha in the kernel of phi, then for all elements in the ring R, R times alpha and alpha times R are back in the kernel of phi. So you can interpret that as saying that R times the kernel of phi, this subset, is contained in the kernel of phi. And same thing, kernel of phi times R is contained in the kernel of phi. So what have we seen? We've seen that the kernel of phi is an ideal of R. So I'm going to pause and erase, and I'll give a few final comments about the relationship between ideals and subrings. I want to end this lecture with a few additional remarks about ideals and subrings. Let's say R is a ring with identity 1 not equal to 0. If I is an ideal in R, and it contains 1, the multiplicative identity of R, then it also has to contain R times 1 for any element R in the ring. But as you go through all the elements R in the ring, because 1 is the identity, you get R is in I for every element in the ring. So the ideal is the entire ring. An ideal that contains the multiplicative identity is the whole ring. So that means if you take Conrad's definitions, where a subring has to contain the identity, and it has to be the same identity from the ring R, then if an ideal is a subring, then it is the whole ring. So what does that mean? That means ideals and subrings are different things. That the only ideal that is also a subring is the whole ring R. So we can study ideals and we can study subrings, but we shouldn't really think about them together. In Dummit and Foote, the perspective is a little bit different. Rings don't necessarily have to have a 1. Subrings, even of a ring that does contain a multiplicative identity, a subring doesn't have to contain that multiplicative identity. In Dummit and Foote, we saw that ideals are subrings, but they're not just any subrings. They're subrings with special additional properties. Okay, so at the end of this lecture, talking all about definitions, I should clarify that I sort of come down pretty strongly on the Conrad's standard definitions for rings document type perspective. I would prefer to keep subrings and ideals separate. I want my rings to have a 1. I want subrings to have that same multiplicative identity. I want ring homomorphisms to take the identity to the identity. But because I want to use Dummit and Foote for exercises for this class, I think it would be very, very confusing if I didn't present both of these perspectives in parallel. So I think sort of going forward in your algebra lives, it's good to keep in mind that some people feel very strongly about subrings and ring homomorphisms having these additional properties as well. But I want you to be familiar with how things are presented in Dummit and Foote so that you're not confused by what homework problems are asking.